Hello, this is Scott Schweitzer. I'm with Xilinx, and I'm one of the technology evangelists over at Xilinx. So today we're going to talk about changing acceleration with SmartNICs, Smart SSDs, and C6. And so let's just dive right in on that. I did a paper that was picked up by Electronic Design back in September on the changes that have happened with the PCI Express 5 bus and some of the protocols that can ride on that bus, like CXL and specifically today C6, and how newer technology accelerators like SmartNICs were starting to utilize those protocols and allow solutions providers or systems architects to build much more complex solutions. And they'll be further enabling this stuff moving forward. So in that paper, I covered a variety of areas. Today, I'm just going to focus on three particular areas, C6 and computational storage and SmartNICs, and then give you kind of a use case that ties all of that stuff together. So without further ado, let's jump right in. What is C6? C6 is a protocol extension for the PCI Express bus that enhances the communications model between the host CPU and adapters that are plugged into the PCI Express bus. It adds not only cache coherency, but a full non-uniform memory access addressing architecture. NUMA has been around for decades. It's very well understood. But what it does is it allows multiple adapters to be plugged into the system and all share a common or eventually a common addressing space, so that a program running on one adapter can actually access memory resident on another adapter through this architecture. And then how disruptive technologies, smart technologies in particular, like smart network adapters or smart storage, are poised to take over utilizing C6 and get more functionality out of the hardware that you're buying. So let's go over the three examples of C6 configurations that exist. We have direct attach, essentially processor to accelerator or processor to memory using the C6 interconnect. We also have switched support, so you can have a switch and then have the processor talk to multiple accelerators or memory blocks through that switch. And then this is the one that's actually the most exciting and interesting because it overcomes a number of challenges that have plagued computers in the past. And that is the whole hybrid daisy chain type adapter to adapter, peer-to-peer communications model, where you have multiple accelerators on the PCI Express bus, and they're talking to each other without necessarily having to deal with the host processor, which sometimes can be a significant bottleneck in performance of applications. So let's use one example technology off the start that's starting to pick up on this stuff. Just earlier this week, actually it was probably last week at Flash Memory Summit, Samsung and Xilinx announced the Smart SSD, computational storage Smart SSD. And what that does is it takes Samsung's leading edge controller and NAND flash storage that would normally go in a 2.5-inch drive, and we add in front of that a big block of FPGA logic, field programmable gate array logic, which are basically computational gates that are reprogrammable, dynamically reprogrammable, and allow you to kind of instantiate a program in gates as opposed to memory access or accessible memory. So anyway, it puts a block of FPGA logic along with DRAM. The FPGA has about 4 gigabytes of its own DRAM for saving states of various different things. And it puts it in a pipeline between the storage and the host. Okay, so that as the host requests through NVMe, which is a storage architecture, as the host makes requests to the storage through the NVMe interface, the NVMe interface is actually executing within the FPGA. That way, as the interface to NVMe evolves over the coming years, all you have to do is flash in a new block, and the drive, picks up that new changes to the protocol and allows you to handle it. It'll take that NVMe request and initially, you could just pass it straight through the NVMe host, which is also running in the FPGA, and then that passes it on to the SSD and flash. And that's how it would work as a normal drive, right? And you'd really see no major value add there other than the fact that the NVMe blocks are upgradable over time. Where it gets exciting is when you can latch in additional computational cores or programs in that pipeline. So for example, you could bring in data analysis where you're doing erasure coding or other advanced analytics to determine what gets written to disk and what doesn't, or what's written to disk as a pointer. You could also latch in a compression block, right? And we've seen cases where textual data that you might find in big data environments compressed a factor of 3 or 4 to 1. And so a 4 terabyte smart SSD would appear to be theoretically 12 or 16 terabytes because of the compression. And then you could also latch in encryption. So that way, if someone were to gain access to the drive, either physically or even tear it apart, they would be able to suss out any of the valuable data because it would all be encoded. And so all of that has been done inside of the Smart SSD. And I'm not going to go over, all the details of that. That's for another day and another time. But suffice to say, it's a computational block in front of the storage device that's actually inside the storage device, and it looks like a normal 2.5-inch drive. Okay. The next smart piece of accelerator technology that is new to most people is SmartNICs. These have come around in the last year or two. Some of them are called DPUs, data processing units. They go by a couple other names as well, but SmartNICs and DPUs are the two most fashionable names at this point in time. I did an article about this stuff back in July. SmartNIC architectures shift to accelerators and why FPGAs are poised to dominate in the space. So feel free to look that up. But anyway, what we've done with SmartNICs is we put another powerful FPGA in front of, between the network and the PCI Express bus on the CPU, or PCI Express bus into the system. And we provide a fair amount of DRAM, getting ahead of myself, DRAM to the FPGA. And then on the back end, we also have a bank of ARM CPU cores with their own DRAM. And we load a SoftNIC instance into the FPGA, as well as other accelerator programs specific for networking, whereas we have the SmartNIC had accelerator programs specific for smart SSDs. With SmartNICs, we have accelerator programs specific to network adapters. We load those in, and things like OVS or encryption specific to networks. We load those into the SmartNIC, and they can then be processed at wire rate as the packets are flowing through. And then the ARM cores can be used for control plane management as well as exception handling. So it's another smart accelerator, just like you might have a GPU or, as mentioned earlier, the smart SSD on the bus. So now if we tie all of this stuff together, we can get a use case like the one shown here. Now I'm going to try and pull something up here. Let's see if I can make it happen. I think it's this pen right here. Hey, here we go, laser pointer. Okay, so in this particular use case, we have network traffic coming in off the network through into the SmartNIC. Let's say that this network traffic is coming from a camera that might be on an assembly line somewhere, looking at widgets that are passing by. Matter of fact, a great example would be a store like Walmart or something, where we have a camera that's looking down on the price scanner, right? And so that video is coming into the SmartNIC, and the SmartNIC can be loaded with a video decode module to take the compressed data that's coming in, turn it into video frames, and store those video frames in a frame buffer on the SmartNIC. So that way it doesn't have to go too far and there aren't a bunch of memory copies. Now, as soon as the frame is decoded and stored in the buffer, the SmartNIC can alert the artificial intelligence machine language engine that's running on the second accelerator, another FPGA card. That would then read the buffer and look for the object that it was being scanned by the price scanner, and it might look at the object and say, ah, okay, I recognize that object. It's a package of meat, and it looks like prime rib, right? And it might talk in concert with the actual scanner to see if, you know, that prime rib was actually ringing up at a prime rib price, or if it was ringing up at a chopped meat price, and compare those two and kick it out. And if it didn't line up, so that way a checker could see what's going on. Maybe somebody switched the price or something like that. Anyway, the AI/ML engine would do that image recognition over here. Once it's done with the frame and the buffer, it could mark that, let SmartNIC know, and then two other accelerators could kick in. The accelerator with video encode over here would kick in. This is a different logic than the video decode over here. That video encode would translate the video for viewing by, you know, let's say a supervisor of the cash registers, and, you know, they may be looking at it on a tablet or a smartphone or, you know, another register. So it has to be available in a variety of different formats. So that would be transcoded here and then sent out to SmartNIC. So once that frame has been transcoded, it could mark it over here on the SmartNIC as dirty. And then once all of that is done, the Smart SSD would also get a copy of the frame from the frame buffer, and it would fetch it as all of these other things are done. And it would then encode it with its own encode, which is designed for long-term storage. So it would encode it at the resolution in which it was recorded, and store that for long-term review later on. So what you essentially have here is you have 4 accelerators all sharing the same video buffer over time, marking it, and you're getting, you know, they'll copy what they need when they need it over, you know, because, you know, they're not necessarily going to want to, you know, they may want the whole thing, they may not. Who the heck knows how the code's written, right? The point is that you're not, you know, bringing the video in, running it into the host CPU where it needs to be decoded. You know, maybe you have something else do the decode, and then it goes back to the host CPU and it gets written in memory. And in this classic model, if it came in and you had different accelerators for each of these and they weren't using something like C6, you would end up with dozens of memory copies as things, you know, are completed and sent back and forth. And this eliminates all of that additional copying and dramatically accelerates the overall turnaround time for the solution. So that's an example of what we can do with C6 and multiple accelerators. And that's basically what we have to say today about C6 and PCI Express. Thank you for your time.